So yeah, hi everyone. I'm Bernát Gabor, and I'll be hosting this tutorial today about the Python packaging ecosystem. And I want to get out from the start out of the way that the structure of this tutorial is going to be focused on trying to present how the Python packaging ecosystem is built up. It's not going to be necessarily how to use setup tools or how you use some of the things we'll see later on. If you are interested in how to use a specific tool in detail, you're probably better off just reading up their documentation and their tutorial section. This tutorial aims more like to give you the big picture and how the various pieces fit together. Okay. That being said, we're gonna look into some of these specific components and we'll try to use them for a smaller example. But generally, we're not gonna be aiming to just do everything. Okay. So that being out of the way, so the slides will be available on that link on the slide you can see. You can just look that up and download them for later use. But the way this presentation can be structured, the slides are going to be kind of like a helpers, where as I'm going to present various components, I'm going to demonstrate them live inside the terminal, just so you can see more how it would look like in action rather than statically on a slide. While I'm going to be doing this, I encourage you to follow along. This is also for generally people tend to understand better if they type them out themselves, learn them themselves rather than seeing, but otherwise it's up to you. I plan to have 2 to 3 sections where we're going to do smaller sections where we're going to do an actual hands-on tutorial where I'm going to ask you to try to do something. But those are going to be a bit later because first we have to kind of understand on what we're building on. So probably in the first 45 minutes or so, I'm going to more like try to give you a picture of the basic building blocks, okay? So who am I? I'm a software engineer at Bloomberg. I work in a team called Data Technologies Quality Control, and I mainly focus on the data ingestion at the company, and within that also mainly on how we can ensure that the data that we collect is of a good quality, doesn't have outliers, has all the nice properties, okay? So other than that, I'm also an open source contributor. There you can see my GitHub account or my blog. On there you can find exactly what I do. But for the purpose of this talk, it's more important that I'm also a member of the Python Packaging Authority, which in practice just means that I maintain projects which are part of the Python packaging core ecosystem. So I tend to give my opinion and use the community and interact with the community to come up with how the Python packaging ecosystem should work and how we can make it better. Okay. And beside this, I'm also the parent of 2 Rorschach Terriers, Silky and Junior. You'll be able to see them here. And because the topic itself can tend to be a bit dry, you'll see that I have spread throughout this presentation a few pictures themselves just to get a bit of relief and something more cute than myself throughout this presentation you can see. Okay, so just to give you an idea, these are the kind of like the projects I maintain. Some of these projects I'm also the main author. The ones which I actually put it with a star. And yeah, let's start then. Let's dive deep into it, okay? So the first question or the main topic we're going to try to understand today is how we distribute code within the Python ecosystem, okay? And generally, I think it's agreed, and that's one of the reasons Python is so popular, that the Python code is easy to read and write. However, just as much as this tends to be the feedback from within the community, the feedback also is that shipping and running that code to other machines is not. And this is what I try to help you with today. I want you to be a bit more hopeful and a bit happier and a bit more confident whenever you try to do packaging and not show the face of this bug on this picture, okay? Whenever you're about Python packaging. I'm not going to promise you that the Python packaging ecosystem is great, but I'm going to give you the basic know-hows to understand where and how things should work, so you know when something breaks, where to reach and what could be the issue, okay? So the first thing we need to understand is what is the state of the packaging today. So I'm going to focus today mainly from the Python packaging authority's point of view. This means that we're going to be focusing from a point of view, how can we ship Python code independent of the platform? Now, every platform, every operating system has its own packaging ecosystem, which might be a bit more appropriate or less appropriate depending on your context. But this is not the type of ecosystems we're going to cover today, meaning we're not going to be covering your operating system packaging manager, or we're not going to be covering Conda. Okay? So in order to be able to actually try to do this packaging, we need a demo problem, something that we can use to demonstrate the packaging story. And the demo problem we're going to be using today is going to be calculating pi. Pi is the ratio of the circle's circumference to its diameter. And one of the easiest ways you can calculate pi is using the Gregory-Leibniz series. This series basically built on this infinite sum. And it states that the p can be calculated, summed up all this series. Basically, every second sum in this series is positive, every second one is negative. And if you add up this division infinite series and you multiply it by 4, you're going to end up with the number p itself. Okay? It's not the fastest, but this is one of the simplest ways to calculate pi, and required around 300 iterations just to get the first 2 decimal precision correct. Okay? Now, here I show you a simple case how this actually might be. For example, here you can see that this is a simple implementation of it. For example, you can see I just use the sign operator, which I switch every every other time, and then I just sum it up by doing that division, and in the end, I just multiply it by 4. Okay, we can quickly actually try this code to actually see that it works, and I'm just going to quickly do that. So let me open up here the editor and try to actually wrangle this into the screen. Okay, let me resize it. Okay. So if I put this in, yeah, just heads up, is that big enough for everyone? And if you have any questions or the answer to that is no, feel free to unmute yourself and speak up. Okay. So yeah, so this is like the simple code. As you can see what we have here, we also do some import, but basically we have this function which takes the number of iteration and returns pi itself. And inside this main section, as we're basically just going to be calculating the 300 and 330 iteration of it, and then just print it out. Okay. So if I do like Python approximate.py, you can see it actually prints that information. Now, on one more thing I have to get out. Generally on the Windows operating system, the way you would start Python is by using the py executable if you are in between a terminal. Okay, now you can also use your editor to run it, but for the scope of this presentation, I'll use the terminal. And you have the py executable, which you can use to run something. And this is basically kind of like an entry point, which allows you to pick and choose your own Python interpreter when you want to, which one you want to run the code with it. If I just py, you can see my default interpreter is Python 3.965. So if I type something here like py, approximate pi, this is actually going to run with Python 3.9. But I can do other Pythons if I want. So for example, if I do here 3.6, then I can run it with 3.6. Now, how this would be different on Linux operating system is usually you have something like 3.9, and then you call that. On the Windows, I don't even have this available, but that's how you would do it. And if you actually like this pi entry point, you can actually use that on Windows too. You want to just look into the Python launcher and install that one. And I'm going to do like, it's a Rust implementation, so I'll just go here. Yeah, this one. So there is this project by Brett Cannon, who is one of the Python Steering Council members. And if you use this one, you're basically going to get this pi executable, not just on Windows, but also on Linux operating systems, such as macOS and so, okay? So that's why whenever I type pi 3.6 just on Unix type Python 3.6 or similar, okay? Now this obviously means that you will need to have that version of the interpreter installed on the operating system, but for the point of this demonstration, more often than not, I'll just stick with 3.9. So all you have 3.9 should be suffice for you to follow along, okay? So another way I can actually use this code that we just written here is I can actually start an interpreter and I can also import it. You can see I can, what was it? P approximate, and it's going to be approximate P, yeah? And then I can call this inside the REPL as that, okay? Sorry, Lisa, which part of it would you like to make it bigger? Is it the Visual Studio one or the? Better? Okay, yeah, so as you can see here, I can also run this code. And I run this code also from the interpreter itself, the REPL, rather than just running it from the console itself, okay? So I'll just answer that question. As far as developing this on Conda, the lift is going to be kind of similar as, for example, using setuptools or Flit or something like that. The core concept how Python works will not change. Conda uses the same principles. So you're going to be able to migrate most of it over one-to-one. But obviously, for example, Conda uses a different packaging logic, a different packaging configuration, but the core of it is similar. It just might have nuances to it. So it's still going to be useful. It's more just that you might not be able to replicate everything one-to-one, okay? And just to give you a bit of a interpreter, so just so people understand better, some people the first question might have is what's the difference between Conda and Python as the Python Software Foundation maintains it. And the main difference is, yeah, I'll answer that, Taslim. The main difference between Conda and the Python interpreter, as you'll get it from the Python Software Foundation, is that the Python Software Foundation aims to ship you the Python interpreter itself, plus Python packages alongside it. Now, some of the packages that you might be using, such as TensorFlow or whatnot, might require other binary dependencies. And these binary dependencies can be, for example, the video card driver that then will drive the machine learning or whatnot. And the Python packaging story does not address the issue. We do not try to ship binaries too. We only focus on shipping the Python code itself, okay? And this is the reason why Conda is a bit more generic, but it's a bit more heavyweight. Conda can actually ship you other executables too. For example, it's possible with Conda to install like TIG itself or other binary applications. The Python story will not address that one, okay? And this is just the case because within the machine learning science where Conda is very popular, it tends to be the case that you have to rely on a lot of binaries, while generally in the Python story, that's less often the case, okay? So, yeah, as Jacob pointed out, what we did here is we import from the pyapproximate module the approximate pi function. And one of the reasons why I did not name them the same is exactly to point out this difference. Like here, you see the name of this file is pyapproximate. So that is the name of the module, but the name of the function is approximate pi. Okay, so those are differences. And those are going to be important, and we'll get to them, just those differences, and we'll just get to them in a second. Okay, let me just go back to my slides. Okay, so if I run this, everything works all right. So back to the packaging story. So how does one make this code available and run it someone else's code? As we just seen it, as you may have just seen it, there's two ways to run a Python code that we've written. One of the way is more, how I would say, someone who is a Python developer would do it is just start up an interpreter and start using imports and run the functions. This is what I call the developer way of using that code that you've just written. Another of the way would be just running it from the command line or within an IDE or whatever. When you just literally say, run this module inside Python, run this file in Python. That is more like the end user way of using that code. And within the packaging logic, there's a difference between these two. The first one, when you run this code as you would be a Python developer, is called as the library way of using that code. And the second way, when you just literally point that file to the Python interpreter and just run it, that's the application way of running that file, okay? Now, there's some differences between these two. In case of the library way, the expectation is that we're gonna expose the source that you just written within the Python interpreter, perhaps on another machine, perhaps on your own machine, and the user will be able to interact with various subparts of the code and can decide itself what I want to run, what I don't want to run. While in case of when you just run the entire file as a whole, then there's kind of like an implicit entry point defined, and only one thing is going to happen. For example, in this case, until I don't change the content of this file, it will always run this logic that I defined it here and nothing else, okay? Now, these two have different needs and requirements, and as we'll see, the packaging story is going to be different depending of, would you like to ship this code to another machine to be used as a library or to be used as an application? Okay, so the first thing, which is going to be like the application mode. In case of the application mode, we don't expect the user to understand how Python works. We don't expect them to do anything advanced. We basically just want to ship them something and they're just going to run it. This is something, I would not say as simple, but always as simple as someone who never used Python should be able to do it. Just install Python, point the Python interpreter to this file, and it's going to print out and going to show whatever you want it. It might print out in this case, or it might start an entire graphical user interface. Okay. In this case, the user needs a Python interpreter. You need to give them all the dependencies. Here you may pin to exact versions just to make sure that the user is running with the same dependencies as you're running with. The code may be obfuscated because, as I said beforehand, it really doesn't matter what is the content of the file. It just needs to do what is defined inside the code. No one's going to bat an eye. For example, if you rename this approximate pi method to X, it's going to work just as far from a command line interface point of view, okay? From an application point of view. The only kind of requirement is that you must define upfront an entry point, and this is the entry point Python going to run once the user starts to run that file, okay? So in case of the library mode, things are a bit different. When you want to share a bit of Python code as a library, generally the expectation is that the other machine will have a Python interpreter, will be able to pick its own dependencies. For example, it might want to use in parallel other libraries, other packages. So you need to make sure you're much more less restrictive with your dependencies, because you want to make sure that two packages which use the same library can coexist at the same time. And then you want to just ship them the code. But here, importantly, it's important that you ship the code as it is written, because the user might access all the doc strings, all the functions, all the variables, everything from the Python file as they are, and they can do this by using the importing system. Generally, standard recommended naming convention using a single entry point. When we go later in the second part of this tutorial into how you package a Python application, you'll see that generally there is a way. But within a file point of view, generally you put your entry point, single entry point within this main section here. But we'll see later on, there's also a concept that generally entry points which can be run are also put inside the main.py file. But as I said, we'll see this later on more in detail, okay? So first, we'll go with the library packaging. And this is also work so that the library packaging is, let's say, the more complicated. Once we understand this one, the application is going to be a bit easier, okay? So the first thing that we need to start out with it, what is a library? A library is a code that can be imported and executed from within a Python interpreter. Okay. So the expectation is that you're going to have a Python interpreter, and you'll be able to import some code from this library and execute it. The first thing that we need to clarify is what is a Python interpreter, to understand this a bit better. And you'll be able to see that there are multiple types of Python interpreters. Usually when people think, when you say Python interpreter, what the people think about is the global or the system Python interpreter. This is the one that you get as installed by operating system package manager. For example, in this case, when I do type in here py, and I can just do sys.executable, you see this is the system interpreter. You can see that its installation location is somewhere on my operating system package locations. So inside the Linux, assuming you don't have any other virtual environments activated, we'll see a bit later what they are. If you type in Python 3.9, this is what would be the system interpreter, what you would get normally, okay? But obviously there are other type of interpreters, and the main type of other type of interpreters are virtual environments. And virtual environments are basically a way to use the Python system interpreter, but isolated from its library dependencies, from its other installations, okay? And there are two ways you can create virtual environment. Well, there are multiple ways, but for now, there are two main ways how you can create a virtual environment. One of them is the VM module. So if I do something like python-m VM, and I do env, this environment that is going to be created is a virtual environment. And this virtual environment will not have the system Python packages available within it. So what it means, if I do py-m people list, you'll see that this is what my system Python contains, okay? But if I do call the Python from within this Python interpreter, you'll see that in this environment, I only have pip and setuptools. I don't have all these operating system packages. So in a sense, this virtual environment isolates you from the system packages, the one that are inside of the system level. Okay. So one more thing, generally people, whenever they use virtual environments, they tend to create the virtual environment as I did here, and then they activate it. Like they can use the activate PS1, for example, if you use PowerShell, or just activate if you use Bash. And depending on your interpreter, you might want to use different activators. And this, what it will mean, what this means is going to do is that this kind of creates another shell in which when I type out Python, this actually will choose the Python interpreter from within that virtual environment. Okay, and here you can see that it's actually from that environment which I just created it. But this doesn't have to, this is not the only way to use a virtual environment. You don't have to activate a virtual environment to use it. If you, I shouldn't have done that. My bad. So if I go back there, you can see I can also use a virtual environment by just typing the Python interpreter itself. And this is basically the same. Okay. So from this point on, the activators within a virtual environment are just a convenience. So you don't have to type out the full path, but otherwise they don't offer any other functionality other than helping you with not have to type as much. Does that make sense? And again, if anyone has any questions, feel free to speak up. If you feel I talk too fast, again, feel free to speak up. The goal of this tutorial is not for me to go through all my slides and finish with 10 minutes to spare. I'm happy to present less, but make sure that what I do present, everyone understands it and is crystal clear. Okay. So another way you can create virtual environments is by the virtualenv module. And let me just do that. So you can see that I have this virtualenv, and I can also do this like env2. Okay. And let's just wait a second. So, and as you can see, this env2 virtualenv is basically the same thing. You get the Python, and it's pretty much the same. So the question might arise, so what are the differences between the VM and the virtualenv module? Why would you use VM or virtualenv? Okay, so this is a quick overview of some of the differences between the virtual and the VM package. But to kind of like go on the highlights of this, the main difference is that the virtual env is a third-party package. What does it mean that it's a third-party package? It means that you have to install it before you use it. While the VM module is a standard library module, meaning that if you install your Python, you should have already access to the VM module. You don't have to install anything else, just Python itself. But with the virtual env, after you install Python, you also have to install on the side the virtual env module. Okay? Now, other kind of like benefits for the virtual env package might be the virtual env package just generally offers a mod badger API. And it also has but that's more important if you're going to write some application that manages virtual environments, creates virtual environments, that kind of things. Also, the virtual env package has a much better configurability story, but there are two main differences that kind of like are, from an end user point of view, the big differences between the two packages. So let me try to create a virtual environment for Python 3.6, okay? And I use the clear flag, which basically means remove the currently existing virtual environment, okay? So if I create a virtual environment by using the VM module, you'll see that once it finishes, if I do env scripts Python -m pip list, the version of the pip and setup tools that I get is 18.1 and 14.6.2. While if I use the virtual env package, and I do like pretty much the same thing, I can just do clear env2. Okay, in this case, you'll see that if I do scripts pip list, you'll see that this one gives me a much newer versions of the Python. So you can see it gives me pip setup tools, which is the latest pip and the latest setup tools, but also gives me the will package too. So as you can see, the difference is that the virtual env package will always give you a mostly up-to-date version of your seed packages. And the seed packages are pip virtual env or pip will and setup tools, okay? So just to give you kind of like a thing, Chris mentioned pipenv. I'm going to tell you that pipenv under the hood uses virtual env, okay? So if you've been using pipenv, in practice, you've been using virtual env just through a different interface, okay? So going back, if you create virtual environments with the virtual env package, your default seed packages is already going to be up to date by default. And there, one of the other big differences between the two things, and this is something you might have noticed, is that creating a virtual environment with the VM module, you can see here like 6 seconds it took, while creating the same virtual environment with virtual env took 2.3 seconds. As you can see, it's more than a 2-time performance improvement, meaning that the virtual env package is much faster than the VM package. And you can see at the subsequent one, it's even faster to the point where it no longer even shows up. It's less than a second, okay? And this is one of the main reasons from end user point of view. Virtual env is faster because it uses caching to make sure that it can perform the creation of the virtual environment as fast as possible, while the VM module is slower, okay? Also, the virtual env package will give you more up-to-date default packages, while the VM doesn't. That's why the case often, if you use the VM package, you more often than what, either you have to pass in the download package, which then reach out the internet to get the latest dependencies. I think it's upgrade actually, not download. If you do this, clear together, or not upgrade. Can't even do that. Okay, so you can't even do that. So basically, the difference is that the VM module going to give you the version of the pip and setup tools that was available when that interpreter was shipped. And this is the reason why I could demonstrate this topic better with the Python 3.6, because Python 3.6 hasn't been updated for a while, which means that the versions of the pip setup tools that you get with them are very old. However, virtual env, because it's upgraded outside of the lifecycle upgrade of the Python interpreter itself, it gets more frequent upgrades. And plus, in the background, it quickly starts in the background it periodically will update your seed packages. And you can read about this more in depth if you want to find out more about this in the documentation of the virtual env, okay, especially on the user guide. And for example, there's a dedicated section about the wheels here where you can see how virtual env ensures that the version of the pip and setup tools that you get is mostly up to date. What does mostly up to date means? It means we'll try to give you the latest version of the setup tools, pip and wheels, which we know are not broken. And the proxy that we use for getting this one is basically we try to give 28 days after the release of a package, and only after that start using it, so that by that time we'd expect within 28 days, if there are any bugs within that release, users would report it and a fix would have been released. Okay. Okay, so that's mainly about the difference of the virtual and the VM module. And generally, I think the rule of thumb is that if you can use virtual env, it's faster, it gives you up-to-date packages. However, if installing virtual env is harder, just fall back to the VM module, it's just as good. Otherwise, the virtual env and the VM package, from a Python interpreter point of view, they create the same type of interpreter. They should behave equally well. Okay, so now that doesn't mean that that's the only way on virtual environments. And this is kind of like more, I don't think this is ready for day-to-day usage, but this is something that you might hear about on some blog posts and whatnot. So just wanted to mention. There's another way where people want to create virtual environments where you don't have to activate them to use them, in a sense that you can just kind of like rely on wherever folder you are. So I'm going to do here a quick demonstration of that. There's this application called PyFlow, which you can use, which creates virtual environments, and let's just say 3.9, which are not using the virtual env way of thinking, but instead they're trying to use, and just to demonstrate this, you can see in the VM case, or the virtual env, normal virtual env case, if you look in the folder, these are the files you see. There's an include, there's a lib, VM, and a scripts file. Yeah. But inside this demo one, if I view it, you can see that now I have a PyPackages folder. And this is more in line with how people inside the Node.js world would expect things to behave when your virtual environment is always present in your current working directory under a given name. In case of the Node.js, this is the node modules within your root folder. In case of the PyFlow, they try to replicate this by creating this PyPackages folder, which contains the same way those dependencies. The main differences in between these two, how this interpreter is created and activated, and where it stores those packages that you're going to be installing it. In case of the VM module, your dependencies is going to be stored inside this lib folder mostly, okay, like this lib. While in case of the PyFlow in it, your dependencies is going to be inside this PyPackages folder, or your package is going to be installed inside that folder. That makes sense? Yes, PyFlow is a third-party thing, and it's not a PyPackaging thing. Inside this, you can actually click on the link. You can click on the link and see it, and it has there some documentation how to install it. It's something to look out for. Probably will require a bit more time to be stable, so to say. But it's a new way on how we should create and interact with Python environments, virtual environments. Okay. So in order for us to understand what it means installing a package, I think what we need to understand is how does Python know if a library is available in portable? Okay, because we say that having a library basically means that I can, once I install it, I'm able to import it and use it. So for us to understand it, how that is possible, we need to understand how can I import something in Python. And the short answer to this, that it doesn't. The Python interpreter doesn't know how to install, what is importable and what not importable. But rather it goes on to the mantra, it's easier to ask for users that permission. So when you type in, for example, here, if I have a virtual environment, just go back, scripts, Oh, go here. Okay. So, oh, it was an older one, but doesn't matter. So if I do type in import setup tools, what happens at this point, Python doesn't know when I type in and hit enter there that setup tools is available or not. Instead, it will try to import it. And if it manages to import it, it's gonna bring back interpreter. And then I have this setup tools object, which is like a module object, which I can use. However, if I try to import something that's not available, it's gonna try to do it. And once it sees that it cannot do it, it will print me an error, okay? So the setup tools that we just imported here is actually a module, and it's kind of like a mapping module, meaning that it has a lot of keys and values in it, okay? And the keys in the setup tools are basically all the functions, methods, variables defined in it. And the values are the actual function, variable, value, variable method. Okay, so for example, you see, I can use the dir function to check all the keys available inside the module. And I see, for example, here that setup tools has the, which one I wanted to show, has, for example, the name key in it, okay? And if I do the dot notation to look up that key, I see that it contains the value setup tools. Or I can see that has the setup, which is a function available on it. But modules are composable, meaning that it is possible to have a module within a module. For example, in this case, you can see that the version is also a module, and it's available within the setup tools module, okay? Now, a collection of modules is what we call a package, and that's why generally we refer to it as an entire, when you install a package, it may have one or more modules in it. But there are some packages that have a single module in it, and that's perfectly fine. Okay, so that's kind of like what happens after you imported things. Okay, so the importing something, it means just bringing something into the interpreter, which gives you access to all the functions, variables, and modules defined within that module. Okay, so just to, there's another way how you can import things, and that's the setup, that's the from notation of the imports. And from setup tools import setup is just a syntactic sugar to basically this other three lines of code, okay? It just basically means import setup tools. Once you import the setup tools, take out the setup name, okay? And just delete the actually imported setup tools module so that in the local namespace, you only now have available setup. You no longer have setup tools itself, the module itself available. So this is like a rough equivalent of it, okay? So basically, we only need to understand import setup tools to understand what's happening inside the background, because the from notation can be reduced from that. Okay. So now the next thing which we need to understand that not all modules that we import are equal. For example, the sys module that you may import, and it even prints it out here, is a built-in module. Okay. Or we have the OS module, or we have the CSV underscore module, or the pytoml module, or the PEP507 module. You'll see here, the sys is a built-in module. The OS is a standard library module. What it means, a standard library module about it, is standard library module basically means that, hey, it's something that's available, it's shipped by the within the Python interpreter itself. And the way you can notice this is if you look at this path here, and maybe the highlighting is not the best, but here you can see that the actual location where this file is, it's right after this Python 3.9 folder, okay? And that means that it's available right within the Python interpreter itself at the standard library level. Then you have also the standard library dynamic load modules, and you can see these are like binary files. And this is just to showcase that it's not only Python files which may be importable. For example, in this case, we imported, as you can see, an SO file, which is kind of the equivalent of the DLL file on Windows or the PyD file from Windows, okay? And then you have the actual third-party modules, and the third-party modules often are available within a side packages path. Like here you can see the side packages path. And within the side packages path, you can have two variants. You have the global side packages path, and you have the user side packages path. Okay, the user is something that you get if you install something with the dash user, and the global one if you install something by just doing python -m pip install. And obviously this here is valid if you use your global system interpreter to install packages. If you install some package into a virtual environment, Python, then things are going to be a bit different. We'll go into that just a second. But now that we know that we can import logic, the execution code can come from multiple locations, it's not a surprise that we'll learn that actually Python has multiple importing systems. And how it works, it has a list of importers registered, and it goes through each of those importers, gives the import value that we want to import it, and we'll ask, hey, importer, can you materialize this import comment? And if the importer can materialize it, it stops and returns. If not, goes to the next importer and asks that importer to materialize it, and so on and so on. Okay, so the system importers, or the list of importers that Python uses, is available on the sys one. This sys meta path thing contains it, and you can see here I actually have a few more, and I'm just going to quickly print this so you can see it. And I write this code. Oh, I think I need one more. Spot the mistake I made when typing this up. That should work. Okay, it works. So yeah, yes. So just to answer it, Jürgen's, we'll get back to Jürgen's question in a bit, but just to go through it. So as you can see, in this case, we have 1, 2, 3, 4, 5, 6, 7 importers registered. And whenever I type in import magic, Python actually goes to each of these modules and will ask, hey, can you import to me magic? First, it goes to built-in importer, then the frozen importer, and then the pathfinder, then to this vendor importer, then to this sys meta package, another vendor importer, another sys meta package. And only after it went to all these importers, it's going to come back and say this error message to me. Okay? So the built-in importer is basically stuff which imports logic from the Python executable itself. Okay? So like the sys module here, actually available in the Python interpreter itself. The code, the machine logic that's run, it's available on the Python executable itself. That's why it's a built-in importer. That's why it's a built-in module. Okay. Then the second type is the frozen importer. This is something that it's not that much used out of the box, but it's a way how a feature provided by the Python interpreter where tools can kind of freeze modules and ship them as that, and then these are imported by the frozen importer. This is something that, for example, PyInstaller is using, and we'll see PyInstaller in the second part of this chapter. But for now, just think of it as something, it's kind of like the built-in importer with the difference that it doesn't actually pull the logic from the interpreter itself, but rather an external location file, and make sure that the code cannot be changed after the import. And then you have the pathfinder importer. Now, 99% of the time you use the pathfinder importer. The pathfinder importer is basically an importer that's available to load materialized code from the file system itself. Okay. Now, the pathfinder importer itself is configured from the syspath variable. Okay. And I can do the same thing for this one, just to print it out. And as you see, there's quite a few paths on the syspath. And we'll see some of this in this order here. But just to say it, so in this case, what we do have is we have by default, the standard library or the default content of the syspath is going to be as follows. First and foremost, you're going to be looking in the standard library zipped location, this lib Python 3.3 zip, and we can see this on the Windows machine here too. You see Python 3.0.zip. And this is basically another functionality. This path importer is not only able to import from the file system, but is able to import from zip files on the file system. So in theory, it's possible to take all your standard library packages or any of your packages, package it together into a single zip file and put it onto the syspath, and it will be discoverable just as much as if it would be available on the file system itself extracted. Okay? This is the standard library zip location. Then you have the standard library directory itself. This is basically, if it's not zipped, look at the file system itself. And then you have the standard library C extension, which is basically all the dynamic which is basically the externals. In this case, you can see, for example, these DSL folders, and we can just quickly see some of it. For example, you can see that the LZM package is defined there, or the SSL package is defined in this file. So if I do like import SSH, this SHL, it's actually materialized from that location, that file. This is kind of like the binary dependencies of the interpreter. And then you have the user side package and the global side packages. Okay. Now, there's just one more thing which some of you might notice. You can see there this empty string at the start of this syspath. Can anyone tell me what is the empty path mean?
Current directory?
Yes. And this is the reason, you're right, it means the current directory. And this is the reason why earlier, when I just started up a Python interpreter, this actually worked. Because whenever you start a Python interpreter, the Python interpreter always adds the current working directory onto the path, and that's why it works. But if I go here and I do like import pyproject, yeah, and this works now, okay? Well, not what I wanted to do, but let me just start that up again. So I import the sys, and the sys path is not static. It's, for me, it's possible to do, for example, remove that one. And if I do the import pyproject, now this is no longer found, because now I remove the current directory from the list of folders the Python is looking to import. Okay? So yeah. Why is an empty string and not a dot? Probably the answer to that is historical reasons. And it's just whoever created it first used and went with that. And then you never can change it for backwards compatibility reasons. Sys.path is the environment variable, right? Not really. You can add additional locations to the, you can add additional elements to the sys.path by using the Python path environment variables. So if you do like, I don't know, A, and then you can do like py-m site, for example. Let me just see if I can do like export or set, yeah. And then I should be able to, now that should show up. I think it might check if it exists. That did not work. But basically, it's you can configure it on the Python path environment variable. Okay. And you can extend additional paths onto the sys.path by using that environment variable. Okay, so with this knowledge, now we can actually answer more exactly what is a virtual environment. So a virtual environment is a Python interpreter that has access to its own side packages. Basically, this allows it to install packages only within itself and not the system interpreter, and shares access to the host built-ins and standard library, and optionally is isolates you from the system side package. For example, if you start up the system Python interpreter, this is what you're going to see. You see you have the standard library path, then you have the user and the global side packages. Inside the virtual environment, the user and global side packages are gone, and instead you have your own side packages available. Or if you use the -- system side packages option, then you still get the user and global side packages, but your own side packages will be injected after the standard library path. Okay. So there's just one more complication. We often mean that you have your own side packages. This is actually not strictly true. The side packages as a thing is just what is the default value for the purelib and the pletlib variables. Because in practice, Python actually doesn't have one side packages. It actually, every Python interpreter has two side packages. And one of the side packages is the purelib and the other is the pletlib. Now on 99%, or not 99, but I would say 80% of the platform, these two are set to the same. And if I start here a Python interpreter, and I can use the sysconfig module to see this, and I do like get path purelib, and I check pletlib, you'll see that this returns me to the same thing. However, if I start up a Fedora, okay, on a Fedora operating system, and I need to do a update sadly here, so I can, oh wait, do I have a Python here? Just need to check. No, I need to update first and install Python. But you see on Fedora, there are different ones. The actual platform library, it's available on the lib64, while the platform or the purelib is available on the lib prefix within your virtual environment. You can see it here. And the main difference, what it meant to be a difference, is that your binary dependencies like DLLs, SOs, PyDs should go under the purelib, while your pletlib, or under the pletlib, while the purelib should contain pure Python code, which is mostly Python code as a .py extension. Okay. Now, as I said, this distinction is there, it's available. And this is something that operating system distributions might decide to use, such as the case of the Fedora or the Red Hat operating systems. But it may also just choose to bypass, like Windows, macOS generally just sets these two to the same value. Even the Debian and dpackage distributions do the same thing, just set it to the same value. So you kind of have the impression that you have only one side packages folder. Even in practice, there's two variants of it. Now, the Python importer system is smart enough that you add multiple times the same path to it, it will deduplicate it. So that's why you don't see the same path happening twice on this sys.path. Okay? So, yeah, this might take a while. I'll just leave it there for now. So, I hope I did not put you on a sleep, and we'll have a break in, I want to say 10 minutes. But before we go there, let's get back to the packaging story, okay? So now that we know that how Python imports a module and where these modules are available on the machine, we can answer what does it mean install a package, install a library. Well, it basically means that you need to provision the correct Python files either into this purelib or pletlib location. And once that is available, basically the import system will take care of the rest. Now, for house maintenance reasons, you also generally package some metadata with your application and some entry points. Entry points are optional, not everything used, but for example, pip virtualenv, these also provide you an entry point. These are like either a UI or CLI, kind of like literal executables that you can run, and they give you various entry points into your package. While beside it, another thing that you might also see inside once you look into the side packages folder is metadata. The metadata, as you can see here, is basically just list what was, for example, the installer used to install this package, what are the files within that package, any other metadata, for example, what are the dependencies of this package, okay? So installing a package, or once a package gets installed, it basically means that the installer will take and give you the Python files in this purelib or pletlib location, will generate some entry points for you if the library is defining some entry points, and also ships you some metadata which describes this package, its dependencies, its files, that type of logic, okay? And we'll see basically in order to generate a package, a library, this is what we need to generate. This is what we need to create. And there are a few ways when we can do that. But, okay, so in case of just to circle back to our Py approximation logic, the first thing that we'll have is that, hey, I want to import this, import once you import it, do that. I have this file. I just want to take this file, put it into the side packages folder, and then put some metadata alongside it, yeah? Because I don't have any entry points in for now in this package. And if I do this and I ship these files to someone else's machine, then they'll be able to both uninstall my packages they no longer want it, and they'll also be able to use it once they start the interpreter. So this is what we'll be aiming for. Okay. Now, obviously, this is what the end user gets, but you, the developer, will have other files on your source tree. For example, you have the business logic file. This is what we want to ship to the other machine. But then you have test files, which don't show up on your installed side packages, but you still have it in your source tree. Then you have, for example, license. You have other like the readmes, other metadata, project management files, or your CI configuration files. And you might also have other files, which we'll refer to it a bit later, which we call metadata based on what your packaging tool is able to actually generate a package for your project. Okay. So basically, our goal is that what you have on your own machine while you're developing the library is going to be the top code snippet, and the bottom code snippet is what we want to ship to someone else's machine. As you can see, we'll move some of the files from our machines to someone else's machine as it is, but we'll also generate some new files, but we'll also not ship some files, okay? And yes, Jürgen, we'll get to your question a bit later. Let's not ruin the punchline yet. Okay, so just to things again. So we'll take, this is our source tree, the development source tree, and we want to ship this package to these target machines. And the way this is going to work, we generally don't tend to ship directly to other machines, though we could. But in generally, instead, we first store the package inside some central package store. And the reason why we do this is that if our developer machine is gone, something happens to it, the target machine is still able to consume this package and install it. Okay, so generally the packaging story kind of like breaks down. I have my local developer search tree. I generate a package. I upload that package into the central package store. I download that package, and then I install it onto that machine. Okay, so, and this is where we'll take 5 minutes break just to give you a bit of a coffee break, and we'll get back in 5 minutes and continue. If anyone has any questions, feel free to shoot it. But yeah. Otherwise, feel free to grab a coffee and be back in 5 minutes. Thank you. Did Hi, I'm back. Just catching up on questions. The reason why I use Windows instead of Linux. I think one of the strengths of the Python language is that it runs everywhere. And because of that, I maintain a few projects, as I said beforehand, like virtualenv or talks. And the aim of the Python packaging authority is to support all of these platforms. So for me, it's just as important to run something runs on Windows as it's run on Linux. So from that point of view, I constantly have to work with all of those. And Windows generally is just a bit more stable. For example, at the moment, I also had a Fedora operating system which break on me. So I have to at some point reinstall it, but Windows just kind of works. So I just went with that. And plus I tend to use nowadays PowerShell as my shell. And I use also Western, which is like a terminal emulator, as my ID or interpreter for the terminal application, which makes it, for me, working on Windows or Linux doesn't make much difference. So yeah. We'll see poetry a bit later, Ryan. Probably I want to say in half an hour or so, we'll touch on poetry and then you'll see how it fits into it. Okay. Yeah, Chris, I want to say your best chance is to probably you will need to recreate the virtual environment. It's probably an odd interaction between VS Code, pipenv plugin, pipenv itself, and virtualenv. I want to say your issue will be with the pipenv bot tracker, but pipenv itself is not overstaffed. So unless you can dig in yourself, it's unlikely you'll have a quick fix on their side. So yeah. But yeah, I mean, pipenv generally, I found it good when you're developing an application. I find it less optimal for developing libraries. That's why I personally, besides just being a maintainer of the virtualenv project, I tend to use virtualenv itself because it gives me a bit more flexibility, a bit more strength when I'm testing libraries. Okay, we'll start back again. I think that was around 5 minutes. So, assuming I find my slides. Okay, so just a quick reminder where we left it off. We left it out with basically, yes, that's going to come up later. We'll go basically how we get our developer source tree to a target machine that's importable. Okay. Now, as we create, we're going to use their interim form, this package form, that the thing that we're going to ship from one machine to another machine. And when it comes to the types of these packages, you can have two types. There is the source distribution and there's the wheels. Let's start with the source distribution. A source distribution is basically what resembles what is on a developer's machine, okay? It basically contains all the files on the developer's source tree, minus a few which are optional. You may include them, but they're not necessarily needed to function as a source distribution. For example, you're obviously not going to need all your project management files or maintainer files. For example, your CI configuration, you might include in your source distribution, but it's really not needed. Or your project management files that you might have, it's also, again, you might include it, but it's not really needed for the purpose of a source distribution. And there's this other, and then it has the business logic, the packaging and tests, okay? Now, this is basically, if you look in our project, these are the files. We kind of say that this is part of our source distribution. But you can see, for example, the CI configuration, we excluded it, and we might decide to not go ahead with it. Now, just before we go further, Jürgen brought it up that there's such a thing as an egg. And I'm going to say that egg is a hard word to say there is such a thing. From the Python packaging point of view, eggs are the pest, and they're practically not supported nowadays. So if you have an egg, you're most likely are working in a legacy environment, and you might want to look up a tutorial maybe 8-10 years in the past. But the Python packaging authority as a whole doesn't really support this egg story. X has been replaced with the wheel, kind of. So let's touch onto the wheel. The wheel is what resembles mostly what we want on the target machine. It contains the installed binary file with some metadata, but it doesn't contain the project management files, any maintainership files, the test files, and packaging files. All these are missing. Basically, in this project, the only thing that's going to be in the wheel from our source tree is going to be the Python file itself. Plus, as you can see, it also contains some metadata alongside it, but none of the other files. Okay. So now, when it comes to difference, what's the difference between having a source distribution and a wheel? From a package installation point of view, and this is the direction the Python packaging ecosystem works, and this is how I find the best way to think about it. We always install a wheel. If you give me a source distribution, the first thing I'm going to do, build a wheel from it. Anton brought it up the question, should stub files, those .py files, be included in a wheel? And the answer to this is yes. And this is mostly when they are used. The Python stub files are used at runtime by the type checker. So, and because they actually need to be present at runtime, they need to be within your side packages platform or Platlib folder or the purely folder. And because of this, they should be within the wheel also, because their usage is at runtime. Again, it's not going to be used by the interpreter at runtime, but the type checker uses it at runtime, or not at runtime, but the type checker pulls it from the Python environment once it is running. Okay, so going from this, so basically generating a package, it means we will have the developer source tree. We're going to build a package. We're going to upload this package in the center package store. Once we generated the package, the consume on the target machine side is going to be, we pull this package from the center package store, basically by doing some discovery and download mechanism. If it is a wheel, we go ahead and install the wheel. If it is a source distribution, then we build the wheel from it. And then we just follow the same line, install the wheel and on the target machine. Okay. So this also answers why you should package ship a wheel. If you package or ship a wheel for your library, it means that there's a lot less work to be done on the target machine, because now the target machine doesn't need to build a wheel. It can just skip that step and install the wheel straight ahead. This is the reason why wheels are much faster to install. There are other benefits that we'll get into this later, that you don't need to worry about other binary dependencies, compilers being available on the machines. But the primary reason, even for a pure Python project, is that if you ship a wheel, the installation will be faster for the user. Okay? So then let's start on the first section, how we build a package. Okay? Building a package, to understand how building the package works, we first have to kind of like, I'm going to give you a brief introduction into the history, just so that you understand some of this concept, understand why we are in the state where we are. And yes, Jürgen, the PyType file should be included in the wheel, because the PyType file is used at the type checker's runtime, and it's pulled from the side packages folder. So it needs to be available in the wheel. Because remember, the only thing that shows up inside the side packages folder is what's in the wheel. If it's not in the wheel, it will not be available within the interpreter installation itself on that machine. Okay, so now to going back to the packaging history, the Python packaging started in the year 2000 with the setuptools package. And the setuptools package was basically the predecessor to the setup.py that we have today. It was introduced back then, and it was basically provided the setup.py file which anyone can write whatever they wanted, and it allowed them to package together Python code. Okay. Now the configuration is Python code, which made a lot of sense then, because it meant that we did not have yet a good packaging story. So the users could come up with their own packaging story. You had infinite flexibility by having a Python file, and you could write anything in that Python file. Then people start to iterate on these two tools outside of the Python standard library. And one of the reasons of this is that it's much quicker to develop something outside of the standard library, because you can release it, test it much more frequent as the Python interpreter release life cycle. And because of this, when setup tools quickly became the de facto standard, everyone was kind of expecting that setup tools would kind of just be available on these machines. And this is the reason why when we create a virtual environment, setup tools is available there, is because everyone was expecting so much that setup tools is available that it kind of like became part of the standard, and it's always provided by any virtual environment creator. Now, wheels were introduced much later. They were introduced in 2014. Until 2014, whenever you installed a distribution, you basically took a source distribution and you installed then the source distribution into your target machine. And obviously, this had the downside that you had to run Python code to install code, which wasn't too performant and also exposed some security reasons or security concerns. So that's why in 2014, the wheels were introduced as a way to speed up the Python installation story and also offer more secure installation of Python packages. Okay. And then at this point, everything was still basically based on the setup.py and running Python files and Python code during the packaging. So in 2015, this project was started, which is called Fleet, which started to kind of like toy around and play around with, can we do a declarative over dynamic type of configuration rather than define what should happen inside Python code, where you can write anything. Let's allow the users to define their packages declaratively, kind of like configuration files, which is easier to understand, especially for new users, and it's harder to get wrong. Okay. And then in 2018, Poetry came, and Poetry is kind of like, the best way I can explain Poetry is Poetry embraces the fact that we should favor configurability or configuration over imperative runtime code running, but Poetry also doesn't want users to understand multiple things. It wants to have a single tool that can achieve everything. And as we see later on, inside even in the previous one, we saw that you could break down the packaging story into generating a package, uploading a package, downloading a package, installing a package. And as we'll see, the Python Packaging Authority kind of has its own dedicated tool for this, kind of in line with how the Linux do one thing, but do that one thing very well philosophy. But Poetry is the other side of the things, is where I'm going to give you a single tool that can give you everything for the better of the worse. Okay. Oh, and by the way, all these links are actually in the presentation are actually clickable. So you can look it up and read more about them if you're interested. But other than that, how the build used to work is basically what used to happen, let's say, before the wheels were a thing, is that in order to, or even recently, in order to build a Python package, you used to use the Python interpreter, feed it the setup.py file, and then just pass an argument what you want it to do. For example, this first one is build me a source distribution. Or the second line here is, this is how you would build a wheel. You can see I just call the Python interpreter, pass this Python file, and then I just pass the command what to do. Now, one of the problems with this is that this actually depends, the success of this story depends on the Python interpreter you're actually using. If the Python interpreter you're using did not have some dependency, it would break. Because maybe you require setuptools 41, but the Python interpreter that you use there only had setuptools 40.0. This operation would break, and would break with horrible errors, cryptic errors that are hard to understand for the user. And that's why in like 2016 or so, we got into how can we improve this? And the solution to improving this are simple. We just visited earlier, virtual environments. Rather than just letting the user use whatever Python they want to do the packaging, we give them a way to actually define their dependencies and then provision these dependencies inside the virtual environment. Okay, so instead of just typing the top one there, in the background, what we want is that we create a virtual environment, and then we use that virtual environment to install the build dependencies. And then we use this virtual environment with the provision build dependencies to actually run the packaging logic. Okay, now this is what PEP 517 standardizes, and it basically introduces the pyproject.toml file. The pyproject.toml file is the standard way, or is the dream of the Python packaging authority. It's where all packaging related configuration would live, especially the standardized parts of the packaging story. Part of the PEP 517, it introduced the file, plus it defined that the required section or the required key within the build system will contain all your build dependencies. So if you want to depend on a given version of setuptools will, or you want any other dependencies during your packaging, this is where you have to define them. Okay, and it uses the TOM file format, and mostly because this is not overly complex, was standardized, and does not conflicted with any existing configuration file. Okay, so this is the build dependencies, which is great, but as you could see beforehand, there kind of like becomes a duality here, because there were two things. Someone has to create this virtual environment, has to install the build dependencies, and then invoke the packaging. And then the packaging itself happening inside this virtual environment. But now we have a backend and the front end of this operation. The backend is the part that actually generates the package inside that visualized virtual environment. And there are a few Python build backends. Setuptools is one of them. Flit is another them. Trampoline is another them. Poetry is another them. PDM another. Hatchling. As you can see, every day there are more and more build backends, and these are Python libraries packages that are capable of, given some configuration file, generate me a Python source distribution and or will. And then there's the build frontends. The build frontends are the Python application or tool that is able to read the pyproject.toml, generate an isolated build dependency, provisioning that isolated build dependencies inside that environment, and then invoke that backend to actually perform the packaging. And build frontends, you have the build tool, which is like unified CLI for backend, but you also have other packages which want to create one comment for all of them. All those also are function both as a backend and as a front end at the same time. For example, Poetry, Hatch, Trampoline, and PDM are a front end and a back end at the same time. They take care of both of it. They can also provision you to build dependencies, but they are also going to build your package. Okay, and pip is also a build front end in this story. So when you type in pip install something, pip will be the one which actually going to create your isolated build environment and then call your backend to actually build the source distribution or the wheel. Generally the wheel if you have a source distribution, and then the wheel is what actually gets installed. Okay, and tux is also another one. We'll touch on tux a bit later. So now once we have this story done, the next story is that, okay, so how does the backend and the front end communicate with each other? And as I showed you beforehand, historically they communicated by the setup.py file and then passing any CLI arguments to the setup.py file. Now, obviously, this had some downside, meaning that every interpreter, every backend needed to actually implement this protocol. They needed to generate a setup.py file just to communicate with the front end. And this kind of like meant that everyone was basically reducing the packaging story to the setup.py file. And to not have to be burdened by that, then PEP 517.8 was introduced, which basically means that we define the programmatic API for the backend and the frontend to communicate with each other. Mainly, instead of using this Python setup.tl this will, we also define a build backend interface. This defines like a package and then a function or a method is what you communicate. And then when you actually want to perform an operation, for example, you want to build a wheel, you're able to actually call methods on that backend operation to communicate to the backend. Basically, the front end generates this Python file and calls this Python file into the isolated build environment when it wants to communicate with the build backend, meaning setuptools or Flit or any of that. Okay? Does that make sense? Questions? Okay. So if no questions, then basically Web 5.7 is just a better interface. It replaces the setup.py invocations with something more standardized. And every backend now defines their own key under which they are available as a build backend. Here you can see a few of them, which location they actually define their keywords. What means for you is that if you use different backends, you need to define this different backend inside this build backend key on your pyproject.toml file. Okay. So, long story short, how to build a package, pick your build backend, and then use pyproject.toml to specify your build dependencies and your build backend interface. Okay. And then just follow the documentation of the build backend, exactly how to configure the backend to do what you want it to do. Okay. Now, obviously, many of these tools actually are also Python applications. So you want to install them to be able to use them. And to install tools, I generally recommend using pypix. And to install pypix, you can use this package called pypix in pypix. And once you install pypix, you can just basically use pypix to install other dependencies. For example, in my case, you can say that if I was going to do this, so I can use pypix and just do install Flit. And as you see, this will basically install Flit inside the isolated build environment. Anton has a question, meaning, does it make sense to use several build backends for one package or just choose one you like? I don't think you should have multiple build backends in the same project. That being said, there might be a story of picking something, one of the simpler backends for something that is a simpler packaging story, a simple story, and a more complicated for someone that is more complicated. In the spirit of like, you don't want to use the most powerful, most complicated build backend all the time, because that would mean that new people who come to that project might find hard to follow it and understand it. Okay? So, what is the, Jürgen asked, what is the difference between pip install user pypix and pypix in pypix? Or have to install pypix in pypix then? The question is, pypix in pypix, and I can go back to this one, it's kind of like a cheat in a sense. So the trouble with installing something in your user side packages is, so if you do just py-m -m pip list, there's the user pypix, this might work, but the problem is this might break some other packages into your user side packages. Because remember, you have a single user side packages. It does mean that if any of the other packages in that environment require a different dependencies, a different versions, it means that you're going to conflict with them and you're going to either break pypix by upgrading another of the user side packages, or you're going to break another packages whenever pypix requires a different dependency when something already does. Okay, so this is why generally, if you want to install a tool, what you want to do, like if you want to go totally sure that you're not breaking anything on your machine, the best thing is to just create a virtual environment. For example, you can do virtualenv VM, okay? And then you can do like VM scripts pip install pypix, okay? And this works perfectly fine. And then you can be cheeky, and now that you have pypix on your machine, you can actually use that to install pypix. Yeah, and I can use like --4. Okay, so this way I installed pypix without actually installing pypix as a user-side packages. I installed pypix inside the isolated build environment, and now I can just remove this VM thing if I want it. Okay, and what I showed you here, these 3 lines of first create a virtual environment, install pypix in that, then use that virtual environment to install pypix, and then pypix can manage itself, because as you see, like I do pypix list, you'll see that pypix actually now also installed, I scrolled up, pypix2, okay? So these 3 steps is basically what pypix in pypix does. It basically just generates a virtual environment during the installation in which, and uses that to install pypix, which then means that after you did this, pypix is now self-contained and manages itself to update to work. And the benefit of this is that you install pypix without breaking anything on your machine. And you get free upgrade of your pypix, because whenever you do pypix upgrade all, this will upgrade all your tools and will make sure that it doesn't break anything on your user side packages. Okay. Now, obviously, as I said, you can do it manually, create a virtual environment, use that to install pypix, and then use that virtual environment to install pypix, or you can just use this command, which does the same thing. Okay. Now, once you install this, now you just want to make sure that you put this path into your path environment. You don't have to. It's perfectly fine if putting it on the path environment, it's not more complicated. It's also perfectly fine. You can invoke it as a fully qualified path. For example, here I can do like, I'm going to do it like fleet.exe. For example, you can see. So that is fine. You can use it as a fully qualified path. But if you just want to type it quickly and easily, you want to put that location of that bin folder onto your path environment variable. Okay. So in next part, we'll actually do some hands-on development. So I would like for you guys to try to package what we had before using Fleet. And for this, I would like to make sure that everyone managed to install Fleet by using pypix or any other way, and they have Fleet available. And I'll give a few seconds for people to try that out and signal back. Okay, so I assume everyone managed. If someone did not having issues, just type it into the chat and maybe we can help out each other. But I'll kind of like go ahead and try to see how this would work, okay? So once you have Fleet available, Fleet is one of these Python packaging backends. But as you can see from this help message, it is also a front end because it doesn't just packages something, it also allows me to build a package, which is, as we discussed, the responsibility of a front end. Okay. It also allows me to publish it, which means it's a more generic tool because it doesn't just deal with the story of the building a package. It's also dealing with the story. How do I upload that package once I have it? It may even install the package. Okay. Now we'll use the init in this case. So we'll just do fleet init to create a project here. We'll say p approximate. That's fine enough for me. As a module name, author is all right. Email is fine. It's all right without a home page. I'll choose an MIT license. And that's it. And basically what happened at this point, as you might see, Fleet generated this pyproject.toml file. As you can see inside this pyproject.toml file, it added a few lines and a section called toolfleet.metadata, which leads you to believe that this tool chooses to store its packaging metadata logic, its configuration within the pyproject.toml file itself. As we see later on, this is not always the case. poetry does the same thing, and in that sense, it's very similar to Fleet. But for example, setuptools has the setup.gfg or the setup.py to actually store such configuration values. Okay, so sure, once you created this, I mean, let me just remove these environments so they don't create issues when I try to package here things. And I need to remove this. Actually, I'm just gonna delete some parts. I basically don't want any of this. I'll delete it. Okay, so I have a cleaner working directory. So I have my, as you can see, I have my license file. I have the Python file that you created at the start, and I have my pyproject.toml file. Okay, so if I do a fleet init, oh, I already did that. My bad. So if I do a fleet build, it even, you can see that the tool even complains what I'm missing. For example, it says, cannot package a module without a docstring or empty docstring. Okay, let's add a docstring if it requires one. So I just add a docstring, my wonderful package tool. Yeah, or my wonderful P approximator. Okay, I have a docstring. I can call again build, complains that, hey, I don't have a version.py. Okay, so it wants a version variable available. I go with version 1.0.0. Cool. And once I did that, you can see that it printed some output, but importantly, you can see in the dist folder, now I have some wheels, okay? So let me go to this dist. And you can see it created two things. It created both a wheel and a tar gili. Let's have a peek what's inside those files. So if I peek into the wheel file, it is a wheel, it's a zip file. So yeah, and because it's a zip file, I can use the zip tool to actually peek into it. So for example, here, you can see that what is inside is just some metadata and the pyproject.py file, exactly what we wanted. And this is what's also going to be installed in that target site packages location. Now, as far as the other file goes, the target file goes, oh, not that's what I wanted. This requires a different incantation to show its content. But this tar-tvf, it will show it that it contains basically all the files, pyproject.toml file, the pyapproximate, the setup.py, and the package info. Okay, so cool. I have all those three files. Both of them seem to contain what I want. Now, that's simple, and we already created our first package. And now we could upload these packages and or just somehow give them to another machine, and the users would be able to use it. For example, if I do a virtual env, I'm going to make actually here a demo folder, and I create here a virtual environment. And in this virtual environment, I use the script ppack install this wheel. You see that will actually install the wheel. And once this installed it, if I start the Python interpreter, you can see I can actually do the approximate import. Okay. And this file is actually now available inside this virtual environment I just created. Okay. So that's all we need. Now, once we have this V file, pip is able to install it. Pip is also able to install the source distribution, and I can just do that. It might actually skip it, but you can see here what I was talking beforehand. When you try to install a source distribution, the first thing that happened is that it installed build dependencies, because the first thing that we do, if you give me a source distribution, I build a wheel from it. And then once I build the wheel, it even printed out the wheel it built. That's what actually gets installed. Okay. So that's pretty much our first package done and dusted. Now, in practice, you would obviously upload this to like PyPI. Oh, Kristinka. So basically, the version is basically this variable that you need to add inside, anywhere inside your module file. See there, 10.0. And at this point, now there's one thing that you might see, for example, which might be interesting, is you can see that by default, the name of this wheel contains py2, py3. Now, what this means is that this file, this wheel, will run both on Python 2 and Python 3. Now, obviously, this is not true, because if you look at this type annotation, you know that this only works on Python 3. So you can see that at the moment, we have a bug in our Python packaging, because this should not work on Python 2. The way you specify if something is working only on a given Python version is by using the Python requires metadata. And to actually see this, I need to look up the documentation of Fleet. Let me just go, because every front end may specify this dependency in a different way. So here it goes. I just build this, and I do something like Python or requires or Python. Wait, I think it's config file in this one. The config file section, and here you can see how you can configure various aspects of your package beside what the init already generated. And for example, for us, what's important is that there was a requires Python configuration here. It's the way, now reading the documentation, we know that the way you can specify what version of Python this merge package requires is by using this notation inside the requires Python. Okay, so let's do that. We just stick in requires Python, and we're going to say it requires 3.9. Okay, and now build again the package. Okay, and now we built again the package. And now if I look into this, you can see that now it actually generated a wheel which no longer contains the py2, which is correct because now this expresses that, hey, this Python file only works on Python 3. Yeah. So that's the gist of it. Now, in this case, as you can see, I use Fleet to build the package, but Fleet, it serves also as a front end and the back end. The dedicated front end for building packages is called build. Okay, and I already have installed it, so it's going to complain me that let me install it. And this shows you that the build project is actually available on the pyproject.toml executable. Okay, so if I don't want to use the field build backend to build the wheel and the wheel, build the wheel and the source distribution, we can see that I can also use the pyproject.toml project, which is a generic Python package builder, to specify that, hey, build the source system and the wheel from this folder. Okay, and this, as you see, is going to take a bit longer. And the reason why it's going to take a bit longer is because this actually needs to install Fleet to be able to do the packaging. Beforehand, when I used Fleet to build the package, I did not need to install Fleet because I was already invoking Fleet, so Fleet was already available. But in this case, that's not the case. And there's 2 runs of this. And you can see like successfully install Fleet core. This is one run, and there's another one here. And the reason why there's 2 run is because the build frontend needs to create separate build environments, both for the source distribution and the wheel distribution. So that's why you see the output of this is twice. The advantages of using the pyproject.build over the built-in fleet.build is that the pyproject.build will always work on any build backend. Some of the build backends, such as setuptools, doesn't provide you a built-in frontend to build your packages. And in this case, you can use the pyproject.build to use. Make sense? Okay, so it installs Fleet because it's referenced by the Fleet. Yeah. So the build frontend goes into this pyproject.tom file, checks this. Hey, I need Fleet core greater than or equal than 4, less than 4. And if you check the output of this, it's actually, that's what it says, that collecting Fleet core less than 4, greater than or equal than 2. Okay. And then it uses this build backend Python API to communicate with the backend that, hey, build me a wheel, build me a source distribution, and that's what is going to put it inside this folder. Okay. Now, one question that Jürgen has, what does the none and any means? And we'll get back to that in a short while, Jürgen. Okay. So once we have this one, the next part is going to be like, maybe we're not happy with the performance of our P calculator. Let's speed it up. Okay. As we seen beforehand, Python is able to import not just Python files, it's able to import binary libraries. And this is what the Python package provides. It's able to take your Python file, generate C code, and compile that C code into a binary file, and then use that module as this C code. And this is quite a big, how should I say this? This is a lot of power, because now I can get a free performance improvement without doing anything. And what happens at this time is that the code I'm going to be running is no longer going to be imported from a Python file, but rather from a binary file. Let's try to do that, okay? Now, the first thing that we're going to run into it is that Flit is not advanced enough to build C extensions. It's not aimed at those users who need to build C extensions. So the first thing we're going to do, we're going to move the project configuration to setuptools. Okay. Now, the reason why I want to do this is also going to show us what are the differences between Flit and setuptools, and to show if one of them is more complicated or not than the other. Okay. So let's try to do this. Give me a second. Do you understand? Okay. So what do we need to do to move this to setuptools? Okay. So the first thing we'll need to do is setuptools no longer contains this configuration in the pyproject.toml. So we'll need the setup.py file to say this is what setuptool uses. And this is just going to have a simple setup in it. Okay. And then we're going to extract out the configuration, the static information into setup.cfg file. And I actually want to do this, but not to look up every configuration one by one from the documentation. I'll cheat here a bit, and we'll actually copy over the configuration from a pre-created one repository. I'll post that into the chat in case you want to follow along. Let me just give not that one. Wrong repository. But what I wanted to do here is to that's the one. I wanted to basically go to, this is roughly what I need. So as you can see, the name version, it's no longer in our description, no longer lives inside the Python file itself. So now we can remove this. We can remove this. The version moved inside the setup.cf. The description moved into the setup.cf. We also defined just a readme edit. The author also moved to setup.cfg. So this no longer is a thing. What are the Python files moved in? We use this thing, which means the packages are dynamically defined. So it means I can remove now this module thing. The classifiers also move to setup.cfg, like this is a classifier. Okay, my requires Python also moved to the setup.cfg. See, I can move it over. Yeah, I'll pass it in a second. Yeah, basically there. See, that's kind of like the end goal here we want to reach. And then we just need to do one more thing. Now we need to, this is at this point, go here. And that's about it, I think. So at this point, if I use, let me just remove the distribution. Okay. So there's nothing in the distribution. So now if I use pyproject, oh, one more thing we need to change, actually. We need to change the build system and the build backend because we changed that too. So I'll just take these dependencies. Let me remove Cython for now, okay? So now, after doing all the changes, this should basically give us the same thing that we had in Flit. But what changed that all our configuration now doesn't live inside the setup.py or doesn't live inside the pyproject.toml, but instead it's split up between the setup.py file and the setup.cfg file. Is this a private? Give me a second because I'll make it public. Change visibility. Public. Okay. Okay, now it should work, the link. Okay, so we moved around some of the configuration from within the source code itself into the setup.cfg and setup.file and changed the build backend inside the pyproject.toml. But post this, once we run the build packaging command, this actually ends up us with the same thing. If I look into this folder, I have a wheel file and I have a py approximate file. Now the exact content of these files might be a bit different because here, pprox storage easy, you see that there are some egginfo files which Flit did not generate. And inside the wheel, we have a few other files. Actually, seems I actually did not include the Python file. What did I mess up here? You see in the wheel, we don't have any Python file actually. Okay. Oh yeah, because I named it differently. Approximate. Okay. If I do my packaging again, you'll see that now it should include the pyapproximate file inside it. Now, setuptools is a bit more verbose. It actually prints what it's doing line on line. So if something's broken, you can actually see this output and debug it to see what breaks during the packaging. But for example, you can see that it actually says, I'm copying this file to this folder. Then I'm creating a tar archive, removing that, all that kind of things. Okay. And now if I do this wheel, you can see now I do have the pyapproximate file part of the wheel. So now with this change, we basically got the same thing we had before. We migrated from Flit to setuptools. Okay. Now let's actually try to speed up our logic. And the way I'm going to do that, I'm going to create here pyapproximate psi. Okay. And the reason why I do this, I'm going to take, just to show you that both of these work in parallel, I'm going to take this Python file and also compile it as a Cython application. Okay. And the way I do it, and this is something you would look up the documentation of the Cython, the documentation of the Cython file is, you just have to specify it in the setup.py file that, hey, by the way, I require you to Cythonize this extra file. And let me go into setup.py. And this is something you can do today with configuration file. So you must put it inside the setup.py file, opposed to everything else. But if you put this one in, and now we need to add to our build dependencies Cython. Okay, so now I also depend on Cython. And now if I build, let's say, just a wheel, save time here, this will actually in the background go out, create the C code for this application we have, and compile it. Did I mess up the naming? Oh, extension needs to be different. I bet. SciX, which is like the Cython extension. Okay. So now we try to run this. We see that this should work better. Still managed to mess up something. Pyproject scipy doesn't match any files. Oh, really good at making typos today. Spikes. Okay. Third time is the lucky charm, no? Oh yeah, you can see. So if I look into the folder now, you see that it actually created a C file. And as some of you might be available, the Python interpreter, the one maintained by the Python Software Foundation, is actually written in C. So if we translate the Python code to C code and compile it and run that, it allows us to do optimizations which make our code faster. So you can see this is quite a long C file, but you don't have to actually understand it. At the end of the day, what's happening if we look into the wheel that we generated is just that from that Python file, it creates this PyD file. And this PyD file is something that we can import and run. And let me do that. Let's go back to our demo thing. And here I'm gonna install what I wanted, but I'm gonna VM scripts pip install this. And let's provide that wheel. And now, if I start this interpreter, Python, and I do import pyproject sci, what happened? That's what I was expecting. So this is a good example I could actually see. You can always check out what was installed. I think I installed it right here. So I think it could be that setuptools did not install it. And I can check by going there and see. You can see like, look, it's not actually there. So what could be here the case is the setuptool decided that doesn't need to install it. So I can do a force reinstall to really convince it that, hey, install it. Oh, wait, no, I know what it is. My bad. I need to install not this version, the universal one, but now I need to install this version. And this is where Jürgen's earlier question came. What is that none and any meaning? Okay. And that none and any is basically the ABI compatibility thing. It basically specifies what Python compilation and endianness is this wheel compatible with and what platform is compatible with it. For example, this one states this wheel is good for CPython 3.9 and also requires Windows 64 bits operating system. Okay. And none and any basically means that it's independent of the Python implementation or the platform. Any is for the platform, independent, it works on any platform, and none means we don't depend on any Python implementation. And CP39 means CPython 3.9. Is that clear? So if I install this one, and I can do a force reinstall just to replace it. And now, if I do a VM scripts Python exe, and I do import pyproject sci, you can see that this actually now imported. You can see, and it's actually backed by this PyD file, which is a binary dependency. I can also find out what importer was used to load it. For example, in this case, it was actually loaded by this extension file loader, which is a variant of what's capable of loading these binary files. If I would approximate that thing. Oh no. If I would use the other one, which was, if I would import pyproject, and I would check the loader on this one, you see that this actually uses a source file loader, okay? So as you can see, different loaders are used to manifest different backend dependencies, but independent of what I use, now both of them are working, and I can use, for example, just to validate this actually works, and I can use, oh, not the item file, approximate file. And this now is much faster than the previous one. Now, here measuring it might be not as easy, so you might use the timey module, but basically here's probably around, let's say, 70 to 80% of performance improvement you can get if you just feed it a raw Python file with basic type annotations to Python and what you get back from it. Okay. Questions related to that? No questions? Okay. So, for example, here is a bit of benchmarking I did by using the timeit module, but you can see from 105 milliseconds for calculating the millionth precision or the iteration, I managed to shift it down to 70 milliseconds. Now, doing this, going down to the sea level does have a downside because it does mean that now I have to generate, now the wheel that I'm generating is only valid for my current platform and it will not work on any other platform. So if I want our users to not have to build their own wheel on their own machine, and in order to do that, you do need to have a C++ compiler available and the header files for Python available, I need to ship a wheel for every possible platform. And you might say that that's not that hard because you have like Windows, Mac OS, Linux, whatever, but it's a bit more complicated then because it also includes potential future platforms which you're not even aware of. For example, when Apple introduced their new M1 platforms last year, those new platform, because it's a totally different architecture, did mean that none of the macOS, previous macOS generated wheels worked for that platform, okay? So there are some downside going down to the binary level, but if you can, but it does offer also some performance benefit, okay? Now, as far as uploading the package, we could already see beforehand, Flit offers just the upload comment, which works. But generally, from a PyPI point of view, the tool to be used to install to the PyPI org is basically the Twine package, and Twine be something like that. Oh, I need to actually go up one. I would just use Twine application to, hey, upload this package, okay? And if, I can also first validate it. I want check, I think it's called. So can you check to check my wheel looks all right for the PyPI point of view? But after that, I can use Twine to actually, and you can see it even has a warning that long description is missing. But after then, I can just use Twine to upload it. And here you might enter your username and password to actually go through with it. Or you might even set up your two-factor authentication or API case, depending on your level of security you wish to have. The example documentation on that, how to do that on the pypi.org website. Okay. So based on that, and someone pointed out it Flit publish. Yeah, but I don't have a Flit project anymore, so it doesn't work. Similarly, the strength or downside of Poetry would be that Poetry is the same. Poetry also, if you check the help of it, has a lot of comments. So you can use Poetry itself to build your package, to upload your package, basically to do anything with your package. While if you're using setuptools, you would have to use Twine. You'd have to use the build project to build one. You have to use Twine to upload one. But those packages are potentially more powerful, especially for C extension. Okay, now that doesn't mean that Flit or setuptools is not going to be just as strong as someday, but we are not there yet. Okay, now on the other side, to actually install packages, we first need to discover and download a package. For human discovery, we generally just visit the PyPI package, as even here was shown, and you have the search one. But what the machine does is not that. It actually goes to the PyPI simple repository API. So for example, to the build project, let me close a few here. For the build project, you can see that I can go to this URL and I can see all the packages uploaded to the PyPI by visiting this web page. And this is what the machine checks. So if the machine doesn't see one of these packages, it means that it's not available on this URL. What more than that, the library doesn't just see this one. What it sees is actually this thing here, the HTML itself. And as you can see, this HTML contains much more than just the links to these libraries. It also contains these data requires entries. So by the front end actually parsing the data requires, it's even aware if some of these packages are compatible with a given Python version or not. Okay. So this is like what the machine actually does to discover and download the package. And then for installing a package, that basically just boils down to extracting that wheel, copying some files in some location, and then just generating the console scripts or the entry points to the application. Potentially, there are other installers available. For example, one of the reasons why virtualenv can be as fast creating virtual environments is because it has its own wheel installer within it that's optimized to work on the wheels virtualenv needs to handle. Okay. So yeah, then just a bit of a bonus content. How would you test your library? Oh, what is diff between pip and pypix? Oh. I think just for Opagani, I would encourage you to, did I share that one? Yeah, I encourage you to compare your Python if you compiled exactly what you had here. So just check that this is what you passed into your setup.py. If not, you could just download that project and try to make that run. That should be correctly configured and should work. I even set up for it some actions to validate it, so I'm fairly confident it would work. Or just compare it with the link I posted in the chat to make sure it works correctly. And you did not have any differences compared to that. Now, the diff between pip and pypix is that pip installs Python packages, while pypix installs Python tools in a sense that it creates a virtual environment and installs a tool with all its dependencies into that virtual environment. So this indirection of creating a virtual environment is what pypix does more than pip. Okay. Now, as far as testing your library, generally how you would test your library, you would first create a virtual environment. It's kind of like what I was doing while presenting this tutorial, is create a virtual environment, build your wheel or source distribution, install your source distribution, and then you would install your test dependencies and then run your test suite. You can see these are like these 4 or 5 comments that you kind of like have to keep in your mind and know how to do. Or better yet, just use this cool tool called Tux, which is basically allows you to define all these type of steps inside the configuration file. For example, here you can define that I want Python 3.9 as my test environment. And I'm going to use this isolated build environment, which is just basically use everything I was talking about in this tutorial, and then define the dependencies, what is the common. And once you do this, Tux will be able to, you can just install Tux and then just type in Tux, and Tux will do automatically all of this setup and run operation. Okay. Opagani, you should not run Python setup.py build. What you should do is you should run pyproject.build wheel. As I said before and earlier, or not wheel, it's generally not recommended to interact with the build backend directly. I don't recommend you to call the setup.py directly. Okay. Like instead of doing Python setup.py build, you should do pyproject. There's this wheel.to and use the build tool, which knows how to make sure everything is set up and working. Okay. So yeah, and I recommend generally if you want to test your library, just look into the Tux tool. It's a great way to declare inside some configuration file how you should set up run for multiple Python environments your project's test suite. Okay. Now, as far as before, it's always publish both the wheel and the source distribution. And the reason for this is that sometimes wheels are banned in various environments. For example, many enterprise environments don't accept installing wheels because they view it as a potential security hole. Also, you want the source distribution to be available when a new platform comes along. And for that reason, you should publish a source distribution just for the sake of being auditable. As far as the test suite, and always ship your test suite with your source distribution so that whenever someone builds a wheel, they can use your test suite to validate that their wheel build was correct. Okay? Was that any questions? If not, we'll take 5-minute break. Everyone grab a coffee, move your legs a bit, and then we'll come back to wrap it up with creating an application. So to answer in the break, kind of like to answer your grand questions, how do you configure that your source distribution ships the test, but the wheel does not? And the answer is, depends on your build backend. Poetry and Flit has the policy that it ships all the files in your source directory, so within the source distribution, but then it uses custom logic what to ship inside the side packages folder within the wheel. As far as setup tools goes, setup tools is a bit more complicated because setup tools by default doesn't ship anything. And that's why with the setup tools, what you do, you often have another configuration file, which is specific to setup tools only, is this manifest.in file. And in this manifest.in file, where you will specify what to include in your source distribution. So if you do something like graph, for example, tests, that would ship everything in your test folder into the source distribution, but would not ship it into the wheel, because what's shipped into the wheel is governed by this find module or this py modules here. Opagani, you want to install pyproject.build with pypix and make sure that it's available. Oh, no, not that one. Actually, I was wrong. There will be an answer. I can say it again because we're in the break. Basically, it in setup tools, the manifest.in file is the what controlling what gets installed into your source distribution or what gets included into your source distribution. So if you include stuff by using the manifest.in, that only goes into your source distribution. What goes into your wheel will be what is defined by the py modules here or the find logic. Make sense? So in case of the setup tools and these tools, the manifest.in is what configures what goes into the source distribution. And this goes both ways. If you don't want to include something in your source distribution, such as your CI files, you would use this manifest.in file to exclude it. Okay. Josh had a question in the meantime that does pip install dash editable work the same if my project is setuptools, flit, or setuptools? Pip install dash editable as stands today only works for setuptools and distutils. Pip install dash editable, it's a non-standard editable install mode. And it's not, it only works with setuptools. Now, Flit may be able to work around this and generate other mechanisms, but it's not supported by the standard ways of doing this. Now, we're not too far to make that a reality though, because the dream here is there's a PEP which introduces editable installs. I want to show it's like 650 or something. Let me look that up. Not 650. Anyway, there's a discussion. By the way, if anyone wants to, or not that one, there's a Discord link too, but if anyone has any packaging questions, problems that you're running into it, your best way or location to ask help is going to be the packaging section within the Python Discuss web server. And for example, here you can see there's a discussion going on for editable installs. And this is what will allow all tools to provide editable installs. So not today, but maybe by next year, pip install dash editable will work the same way for all the backends. Yeah. Just looking, trying to find the, oh, maybe let's start. But this is a PEP, it doesn't have a number yet, which actually tries to come up with a standardized way how to define editable installs, but there's not defined yet. When would it end? We started a bit later, so I was hoping for a 15-minute extension. But if you have to leave, feel free to leave. I personally will try to use an extra 15 minutes just to go through what we have left, okay? Okay, is there a reason to still use the pyproject.toml file where everything is in setup.py CFG? Yes, you can put everything in the setup.py and setup.cfg. This part, the build system definition, the requires and the build backend must be in the pyproject.toml file. Now you can move everything else out of it into the setup.cfg, setup.py, but these two must exist here. And there's also a standard which was introduced a few months ago, which aims that wants to provide the standardized ways inside the pyproject.toml file. So old backends may use this pyproject.toml file where they define their build dependencies, that kind of stuff. That's probably going to take a few years until all the tools adopt it, but maybe in a year's time, it will be possible to actually drop both setup.py and setup.cfg and still use setup tools and put everything in the pyproject.toml file. That's where we're kind of heading, but we're not there yet. For today, for setup tools, still keep using setup.py, setup.cfg, and pyproject.toml together. Okay? So,
Bernát, I'm sorry. This is Pagani, Oscar. The question that I have is right now when I try to do pipx install pyproject build, it says it has version none. Do I have to put it in the manifest?
I would have to have a look at it. Can you reach out to me after the tutorial and we can discuss that, okay?
I just put it in the chat and then we can talk, yeah. I'm just going from GitHub. Exactly.
Yeah, no worries. We'll get back to you after the tutorial because might require a bit more debugging, okay? Okay, so going into the creating an application. So as I said before, this is what you had for the library. And this more or less works great, but let's look, what about an application? Now, as for application, we touched on beforehand, is an application runs with the latest compatible, or library runs with the latest compatible dependencies. mostly because it might need to coexist with other libraries that have different version dependencies. It need to, that's why it tested the latest compatible dependencies just to make sure that it wasn't broken, and need to expose all model features as they are, and needs to be installed. Actually, with an application, this is not the case. It doesn't need to be installed because it doesn't need to be discoverable in the Python importer system. And it's fine to run with a single type set of dependencies, doesn't need to run with the latest dependencies. And test with the given set of dependencies is totally fine. The application needs to expose only a single entry point. It's not the case that you have to be able to run any functions within that Python file. And ideally should just be as simple for the end user, just, hey, download this file, copy this file and execute it, okay? So one way you can actually ship your application is to treat it as a library and just use the library's console entry points and GUI entry points. The downside with this is that you need to understand, the user that's using your application needs to understand virtual environments to actually make it work, and potentially to, if something breaks, needs to understand virtual environments to fix it. It needs to know where those entry points get generated, the console and the GUI entry points. It needs to know, which might require them mangling their own system path, which might be a bit of advanced functionality. And the dependencies, in case of if you treat it as a library, are not pinned, meaning that you might have a different dependency than user that's running, and that might not work at a later time. Now, you can still deploy your application as a library if you manage to solve these issues by using another system. For example, if you build a Docker image and you give this Docker image to the user, then it's perfectly fine to ship your application as a library. Treat it as a library, install it as a library, and then just this frozen Docker image is what's going to be given to the user, and hey, just run this Docker image. Okay? So the way the Python story around this goes is basically zippapps. And zippapps is basically this functionality which we could have seen before. We saw that Python is able to import files from within a zip file. Okay, and this is what the zippap allows you to. Basically, I can create all the files of my project, put it inside a zippap, and if I give this zippap to the Python application, to the Python interpreter, the Python interpreter can run it because it's just going to put the location of the zippap onto the sys.path. And after that, all the files within the zip file are discoverable. Okay. And a lot of these tools that we're going to see just in a minute basically leverage this functionality. Now, this is what the virtualenv project also does. For example, if you want to use virtualenv without installing it, because maybe you don't have rights to install it, you can basically just download this package from virtualenv. And what you're going to end up once you download this package is you can put a Python interpreter at it. And as you can see, for example, it runs happily ever after. And this is like a Python zip application. Okay. Now, if you look inside this file, the zip application, you will see that it basically contains just Python files as there will be on the file system. They're just put together inside the zip file. Okay. Now, one important thing is that the zip file always has an entry point. The entry point is the main.py file that you package within the zip.file. So the entry point for this virtualenv application is basically the logic that gets executed when this main.py file gets executed. So if you want to know what's happening in this main.py file, I actually want to maybe, let's see, unpack this, and I want to look into this main.py file. And you'll see here, there's a run entry point, and then it just starts running from that point on. Other than that, it behaves exactly the same as this file system structure would be extracted to the file system. Okay. So easy way, we just take everything that we have in our application, put it together in a zip file, send the zip file to the user, and just tell them, point your Python interpreter at the zip file. Okay. So simplest thing, let's try to do this. Let's try to actually package this. I can, for example, say I need a folder, and I'm going to create for that make there zip, and I'm just gonna copy the Python file into this zip folder. And now I can do something such as similar as this. So I need to specify the folder in which my files are located. So in this case, it's in the zip folder. And then I need to specify the module inside which my entry point lives. And then I need to specify a function that gets executed, called when I run it. Something like that, okay? Now it complains that this entry point doesn't exist, and for good reason, because if I go into this zip folder and I do this pyproject.toml, I'll see that there's no run in this, because this relies on the fact that this name section gets run when the file is executed. But I can just move that into a run function. And if I do now, the zipping, oh, I actually have a dot in here. Now it should work. And if I do now this zip python, this actually runs. And now the entry point actually runs this run method. And I can investigate again this. If I just do inzipzil python, you see that it generates a main file, which actually just calls that run method within it. Yeah, so if I just do like a look into this main file, you see exactly that. Based on this configuration from here, you just generate that main file and then puts this zip file onto the path and just runs it. Okay. Now, the only kind of like problem with this is that, as you say, this zip file doesn't contain its dependencies. Okay, so like, what about my dependencies? I might have a lot of dependencies, which I might also need to ship to the user. And the zippapp, as out of the box, doesn't do this, but there are these other tools called pex and shiv, which we're going to see in a moment, which do this. What they do offer extra besides this packaging logic, what zippapp does, is that they also deal with your dependencies. It's going to look at your application. It's going to discover what are my dependencies. For example, here's the pex one. And it's going to package your dependencies also into the zip file. And this zip file will also then provision at the start of the zip or the Python interpreter so that it's able to load this, for example, here, the wheel files. Okay, you have either the pex as a solution to this, and then you also have shiv as another solution of this. And here, if you go to, for example, you can see, well, actually, let's give it a quick try to with shiv. Shiv actually is able to package, it's able to, let's go into it. It's actually able to package something that you already published. So I can specify to the shiv that, hey, create a zippapp file for my, for example, for the virtualenv project and put it into virtualenv.shiv. And then here, the second virtualenv means that my entry point is used as an entry point, the console entry point called virtualenv. Okay. If I run this, what actually happens in the background is that now I end up with a virtualenv.shiv, and this virtualenv file is a zippapp file, meaning I can feed it to a Python interpreter and will actually work and run. And if I look into the structure of it, I can see that it actually took all the dependencies this application had and put it inside the zippapp file onto the side packages. And all my dependencies, even the binary entry point executables, are available there. Okay. So pretty much this is it. And then it just defines its own environment, just some bootstrapping logic, which just makes things that whatever you see here, it's actually available for importable inside this main.py file. Okay. So yeah, if you want to just literally have a Python file and you just wanted to give it to someone else to run it, and you don't want to actually look at it, either using pix and shiv is great to give them all the dependencies packaged into one single zip file. They can just point at it and run it. This is fairly simple and easy to use. Now there's another family of installer generation, and this is the PyInstaller. PyInstaller is different in a sense that PyInstaller doesn't just generate you a zip file, but it doesn't just packages your own application, but it actually packages your application, the Python interpreter, together into a single file that's executable. Like this is kind of creates literally a executable file that you can copy around. For example, if we go back, okay, and we have this pyapproximate or approximate file, this file, okay, I can do pyinstaller -f thing. And if I run this pyinstaller tool, you'll see that once it finishes, it actually goes out into my file system, finds my Python interpreter, finds my binary dependencies, and puts all them together into a single file. And I can check it out inside of this bush, and you'll see this pyapproximate exe, pyapproximate exe. And I can actually check its size. You can see it's fairly sizable. It's 7.2 megabytes, because actually also packages the interpreter itself into that. But the advantage of this is that now it actually can be run as an interpreter itself. And now this actually doesn't work because here I did not actually allow this to run. So I need to do something. Oh, I undid this. There's this name. Let me just copy it. I need to actually run it so you can see that it works. Okay, so because it's going to run this pyapproximate file itself. So if I do this again, and it regenerates that executable, you see that it's actually going to work. And now this actually generated an executable. Still did not work. What did I do wrong here? But it should at least generate. Not sure what, but generally the idea is that it will generate you an entry point, which you can then just literally give it to someone and ship it. Can you run a PyInstaller on Linux to create a Windows executable? The short answer, no. And it's even more complicated than that, because what basically how PyInstaller works is whenever you invoke it, it goes out, checks all the Python files that you're using, discovers all the dependencies, both Python dependencies and binary dependencies, and collects them together into a single package, and then it ships this single package. And whenever you actually start here, I started here like pyapproximate.py, this actually unwraps all the files this project was using into a temporary folder and runs it from there. And because it collects the binary dependencies from the platform it's running onto, it means that it's only able to run on the same platform where you built it. Okay. If you just want to, and this makes it fairly easy to run, I would say if your friend is total new and doesn't know Python at all, I think PyInstaller is a great way to package your application. There are some edge cases you might run into it and rough edges, but generally it lands you with a single executable that you can just give it to someone, and it's simple enough that they could just literally run it and it would do what you expect them to do. If they know a bit of Python, I think the zippapps are a bit more robust. They're less rough edges you're going to run into than with the PyInstaller. But it does mean that now the user has to know how to install Python and how to invoke Python applications by passing the zip application to it. Okay, so my general consensus is that PyInstaller is a bit stronger in a sense that it makes the barrier of entry lower for the end users, but be prepared to run into more issues about using it, just how intrusive and how it works because of that. While the zipapps are generally much more robust in working and behavior. But if something goes wrong, it's going to require you more expertise to debug it or use it. Okay. So this is one bonus content, just kind of like a thing which you might be wondering. As you said beforehand, the virtual env actually has differing versions depending on the Python you're using it. For example, you can see on 3.9 and 2.7, totally different type of Python dependencies are needed. So one might ask, how is capable virtualenv in packaging all their dependencies inside a single zip file? Because as you might have seen before, this virtualenv.py, this works the same way if I call it with Python 3.6, or if I call it with Python 3.8, okay? Because both shiv and the PyInstaller and the zip and the packs, they always only generated the package that is guaranteed to work on the exact interpreter that you built it on, not in a different interpreter. And this is just kind of like a showcase that how you can reuse some of the power within the Python ecosystem. How you can make this happen is that the Python or the zip application that virtualenv ships actually contains multiple versions of multiple dependencies beside the actual source code. For example, you can see it contains 1.1.3 of import lib metadata and 1.6.1 of import lib metadata. And it has these distributions and models.json, which might actually look at it. And these distributions and models specifies for this Python version what is the exact versions of the wheels that actually are used for. For example, you can see for 2.7, a lot more libraries are used and different versions than from 3.9. Okay, and the way virtualenv is able to dynamically load the correct version at runtime is that at startup, it basically loads this kind of like lookup table, which is defined inside the models and distributions.json. And based on this lookup and the current version of the interpreter, it installs custom importers, which resolve to different paths depending on the Python versions you're running onto it. So this way, you can actually have multiple versions of the same library packaged into the same zippapp application. And for this, you just need to have a bit of look into the PEP 4.5.1 and 3.2 with the import hooks and how the import system works. But if you do that, and let me just quickly unzip this, you'll see that, and we can have a quick look at this before we finish this up. You'll see that basically what's happening is that you can register custom importers that are able to find the models and load the models dynamically based on this version information. And these are just basically registered and added to the system meta importer path at the start of it, whenever this Python interpreter starts up. Okay, so this is just like a nice way of how you can mix what we learned about the import system earlier in this talk or this tutorial and the meta path. And I encourage you, if you want to like understand it better, look into this. It's a good use case to see how you can mix those and how you can actually create single zip files which are cross-platform compatible potentially. Okay, and after that, that was basically all I had to take. So I'm happy to answer any questions or issues people ran into it. So yeah, just speak up if you have any questions. I'm happy to answer them. Otherwise, thank you very much for your confidence and your time you gave me today in this tutorial. I hope this was very useful for you, and thank you.